right. I think we can get started. I see a couple of folks still joining, but it's 11:30. I think we can start. So welcome everyone to our session. My name is Maximilian Schellhorn. I'm a senior solutions architect with Amazon Web Services, so short AWS. And this is my colleague Dennis Kieselhorst. So we structured the talk into two sections. So I will cover the first part where we talk a bit about more the conceptual kind of underlying groundwork for event-driven architectures in general and show you an evolution also of Amazon.com. And then the second half, we will have Dennis showing you the real-world implementation and give you some GitHub repositories so that you can get things started. I want to emphasize a bit the title, so it's phrased as getting started, right? So if you're already deep into distributed systems and have been doing a lot of that in the last couple of years, there might be not that many new things for you, but rather a reinsurance of things that you probably already know. So really focus on getting started freshly with event-driven architectures. And the title says 2023, but I would actually like to start a couple of years back in 1995, where Amazon.com actually looked like this. It already had like 1 million books by then, and so it was already the Earth's largest kind of bookstore. But as you can see from the design, right, it was even before HTML tables were a thing, so it was quite of a modest beginning. Now, if we zoom in a bit on the underlying architecture, you can actually see an application called Øredev, which was a single C binary. And you might be wondering, Øredev, right, why is it named like that? So a bit of trivia here. Inside Amazon, usually services are also named in Portuguese or cities like in Brazil. And Øredev is actually the narrowest part of the Amazon River. And therefore, since all the traffic went through that kind of service, they thought Øredev might be a good name. So you can see everything was stored in a single database, so customers, orders, inventory, everything was stored in a single database. And obviously a distribution center had to be notified to then ship your package back home. Right? So, and in the beginning that was fine, right? But if you would add new functionality, for example, in 1997, we added like a buy with one click kind of option, all the changes have to be made in that single kind of C binary. So there were even rumors that it take like 12 hours to build that kind of binary. So you can imagine teams were also quite blocked and they were kind of relying on each other. And also independent scaling obviously becomes an issue here, right? So what if the orders basically need to scale out a lot more than maybe a customer or inventory service, for example, right? And also the same for failure resiliency. Maybe I want my orders to have a different kind of availability than some kind of a backend kind of service that I don't need that often. So Amazon at that point needed to scale, right? And therefore, a couple of senior engineers in 1998 wrote the Distributed Computing Manifesto. We've released that actually last year. So here with the QR code, you can take a look of what they have come up back then. And the goal was to create a new architecture to accommodate the growth of Amazon. So by that time, they wanted to have a system that would be able to handle 10 times more the orders that they currently do. So it covers a variety of topics, right, which were quite innovative at that time. But one important point I wanted to highlight is the move to a more service-based architecture or service-oriented architecture, right? And those kind of services, they would only be allowed to communicate via well-defined interfaces. So if we go back to the initial architecture, what happened at around 2000 was that Øredev was broken up into multiple independent services, right? So for example, there was a new customer service that kind of was independent, and if anyone needs something from a customer, right, it would expose their kind of API and they can call that via that interface, but not directly going to the customer database, for example. And it has a couple of benefits, right? So first of all, customer service can scale kind of independently of all of that. You might have faster release cycles because you have an own team basically just taking care about the customer service. And also in terms of resiliency, right? If there's an issue with any kind of other part in the system, right, the customer service, for example, would still be running. So fast forward a couple of years, in 2006, Øredev was completely broken up into a thing called Garupa. And Garupa is actually the part of the Amazon River where everything fans out again, right? So there was also a relation between the narrowest and now the evolution of that kind of architecture. So when we follow this principle, what we get is we're getting more and more services, right? And obviously those services, they need to communicate with each other somehow, right? They need some kind of different data of each other. And for example, here you can see the track shipments, right? Maybe need some kind of product details or reporting defects, need something of where the actual product was stored, for example. And what you're ending up is you get like a web of microservice. And if we go back to our example and fast forward even more a couple of years, we can see a lot of things happened at Amazon. So here in 2023, for example, this is the architecture currently. So every single dot is a single service. So currently we have like tens of thousands of microservices running at the moment. And also it's like a much different scale than we used to. So for example, on the Prime Day this year, we had like more than 100,000 items ordered per minute, for example. So you see the initial beginning, you kind of had to be ready for that kind of load. And if we zoom into that actually, right, we can see here that obviously services needs to communicate again, right? So this is a single service that basically needs to communicate with like 300 other services, or the other services are actually relying on that kind of service, right? So we are asking, how can those services actually communicate, right? And I think the one that is like we are all very familiar with and that has been around for a couple of time is like synchronous HTTP kind of microservices. So let's say we started splitting up like multiple services in their well-defined boundaries, right? And then we realized they need to communicate. So let's say we're creating an order, right? And we need to create an invoice. So the order service could directly call the invoice service, and the invoice service creates the invoice. It says 201 created, and then the order service returns back to the user saying the order is created, and as well as the invoice service, right? So you deploy that and it works actually great, and it even has like a couple of benefits, right? So usually they reside in the same kind of network, so it's usually quite fast, the communication. It's quite simple to implement. It's just like a basic HTTP library, for example, doing like another call, and you can also fail fast. So if the invoice service has an error or something, right, the order service could immediately return back to the user also saying there was an issue. So if everything works smooth and everything is fine, right, so why should we do anything different in that kind of problem space or architecture? And the first problems actually arise when we're adding a bit more of complexity, like we're adding new services. We want to also fulfill the order. We want to call a payment service, maybe like some kind of loyalty card or something like that. And I think this is a natural evolution of architecture in general, right? There is an evolution, we get more services, they need maybe some kind of information from each other. What is more problematic in that kind of case is if you would implement that with kind of a synchronous HTTP communication, because first of all, the order service in that case would need to know about the location of all those services. There needs to be some kind of service discovery, right? Where is that exactly? How do I call it, right? How does the structure of the request essentially look like? What is the format? What are the routes? What are the return codes that can I expect, right? So all of that, basically the order service would need to take care about. And what if even if one of those call fails, right? So the order service would need to think about some kind of appropriate retry logic, right? Do I retry 2 times? Do I retry 3 times? Do I retry 10 times? Do I retry forever? Do I back off between those retries, right? Do I wait 10 seconds, 20 seconds, right? And so on and so forth. And probably I even have some kind of background thread or something doing that work. And not even about failure, what about also service degradation, right? So let's say this service, it needs like 10 seconds for some reason. Do I really want to wait for that kind of 10 seconds? Do I fail fast? Do I have a timeout, right? And is it actually needed or a requirement for the order service to know anything about the loyalty service? Should it block the order from being processed, for example? And yeah, systems tend to get even more complex, right? So that was just the first layer after the orders. What if I have additional kind of layer that need to communicate between each other? And yeah, that's a natural kind of evolution, right? And there might be even more services being interested in the ordering service. And we can obviously not rely on the ordering implementing with all of those new kind of features that we might want to request. And it becomes also a bottleneck for the development teams because you have a very high kind of coupling to the ordering here. And now we talked a bit about like kind of the problem space, what are like common issues and that kind of setup. And now we want to focus now a bit more on what would be a potential solution of that design. And here we are talking about event-driven architectures, right? So for us, or our definition of event-driven architecture is an architectural style, right, of building loosely coupled software systems that work together by emitting or responding to events. And I think the most important parts here in that kind of definition is that's an architectural style. So it's not about the technical implementation. So it's not EDA is Kafka or EDA is SNS or EDA is EventBridge, right? It's really just about decoupling system, and it's more like a general kind of conceptual topic. So loosely coupled means we don't want that services call each other anymore directly. And events means, so systems emit in response to events means that, yeah, emitting events and responding to events. So when we talk a lot about events, what does that actually mean? So an event is basically a signal that a system state has changed. Okay, so let's get a bit more concrete. So how can that look like? So here, for example, would be just a simple JSON structure of an event, right? So it usually has some kind of type. So it's like order created. It can also be order updated, order deleted, and so on. And it contains some data that is related to that kind of event. Okay, and they usually can come into different kind of flavors, which is kind of important also if you think about the downstream services. So you can think about sparse events, so events that only contain very minimum information, right? So the order ID 123 has been created at timestamp by customer 456, right? Maybe that's the customer ID. So if you're focusing on sparse event, that means you're pushing some of the responsibility maybe to the downstream services because they might need to query back some additional kind of information later, okay? And the second part would be more of a full state description. So you can say, okay, I put the order IDs in it, the timestamp, but the status of the order is open, the total amount is that, and the customer name is that, and the address is that. So with that kind of event description, the downstream services would have all the information that they need, maybe to do some kind of shipment, for example. So if we go back to our initial example, so what would change? So instead of calling services now directly, we would publish the event as we just described, and now in that time we would submit it to an event broker. So the event broker here acts as an intermediary, and we will talk more about the functionalities here. So the downstream services, instead of receiving that directly, would now only implement or basically integrate with the event broker in between. And that has a couple of advantages, right? So first of all, the order service does not need to know about any service that is on the right side here, right? So it just says, I had an order created, that's it, I'm out, okay? And the other stuff basically is handled on the consumer side, right? So also here the event broker acts as some kind of a buffer, right? So if you think about, so the event brokers, they sometimes have things like durability. So messages are stored, they can be maybe even replayed at a later time. So if the loyalty service, for example, goes down and cannot process, it can come up again at a later time and start the processing from where it has left before, okay? And that also really helps in retry and error logic, right? So it's not up to the left side now to decide when to retry or how to back off. Actually, the right side in that kind of scenario can decide what is the pace, how fast do I want to retrieve those events. If I can only process 10 orders per second on the right side, right, they can kind of do that at their own pace, while before the order service might keep hammering the dependent downstream service. And if you think about also from a business perspective, you're also getting a lot more extensibility, right? So let's say you come up with a new kind of feature or a new service. The only thing that you need to do is you would listen to the existing event broker and you start receiving events related to the order. So it's like quite extensible also for the future. Now, where there are advantages, obviously there are also a few kind of challenges, right? So you need to think about eventual consistency, right? So the order service does not immediately know if the invoice now has been successfully created or not, right? So how does it know that? It does not get the direct feedback anymore. How you could implement that, right, would be, for example, the fulfill service emitting another event saying order 123 was fulfilled, and the order service initially could subscribe to this event kind of again, and then is notified that that happened. But it's not immediately. So it's also adds a bit more complexity in the front end, right? So how would you display that if the invoice gets only created after 2 minutes, for example, right? How do you display that to the user? Do you want to implement some kind of WebSockets that you can send a notification also to the client to show that, okay? So it just adds a bit more kind of complexity also, because things will happen, so they will eventually happen, but they are not happen immediately, okay? So as we've seen now, again, a couple of benefits, and I want to summarize that even more with a quote that we have. So if your application is cloud native or large scale or distributed and doesn't include a messaging component, which can be a broader kind of description of an event broker, that's probably a bug. Or as my SA colleague in Germany likes to say, friends don't let friends rely on synchronous integration. And I think he is right, because event-driven system really gives us a lot of freedom in the future and our architectural kind of decision, right? So we can evolve our architecture. We can add additional producers to that. The producers don't only have to be applications, right? It can be maybe change data streams from a database, right? That can be automatically integrated with the event broker. Or it can be IoT devices, right? All kind of different producer scenarios we can think about. And on the event broker side, right, they also come with a lot of capabilities. So there can be extensible kind of routing mechanisms. So maybe if message contains X, I route it there, for example. They can have, as I mentioned, durability. So you can store messages for a longer time, right? So even after half a year or something, right, the messages would still be there for a new service, for example, to pick up. So there are a lot of things that you can think of what an event broker gives you. And on the consumer side, as we said, you are quite flexible now to evolve your architecture, right? So maybe you're hooking in new analytic services that do some kind of calculations on top of the events that you have on the broker. So you can think about even new business cases without really interfering with your existing architecture. And now, before jumping into the implementation, and Dennis shows you a few concrete examples how you can implement that, one thing I want to highlight, and it sometimes is misunderstood, right? So we often get the question, so I just put a queue between all the services and I'm done, right? So not quite. So there are a couple of different ways, actually, or different types of channel I want to highlight, because it's emphasized a bit on how your solution might look like. So first of all, you might have a point-to-point kind of queue channel. So and that's usually you would use that just between two services, right? So think of here, the sender could be the order service, for example, and then you want to have some kind of processor, the receiver, which would be the invoice service. And usually in a containerized environment, you would have multiple instances of this invoice service, for example, running, right? And in that case, each instance would only retrieve a subset of each message, right? So only each message is consumed by exactly one of those receivers. And on the other hand, and which is more a bit into the event-driven nature that we just talked about, is the publish-subscribe kind of pattern, which usually works around topics, where you put messages on the topic, and all messages essentially will get routed to different kind of subscribers, right? So it can be the invoice service, the fulfillment service, and so on and so forth. So therefore, each message is consumed by each kind of subscribers. And with that, I would like to hand it over to my colleague Dennis to show you a few about actual implementations of that topic.
Yeah, thanks, Max. So obviously, what's the first thing you need to do when you want to start implementing it. It's buying a product that does all this fancy event stuff. No, I'm kidding. It's obviously you need to be clear about the events and the business use case and everything behind that, but we will not cover things like event storming that you heard in another session this morning or domain-driven design. This is what needs to happen beforehand. But then when we get to the technical implementation, it's obviously that we need this event broker that we have seen in the middle. And as we work for AWS, of course, there's an AWS service for that. Is that the only option? No. But let's start with that because it's pretty simple, and those services are pretty mature because they exist for a long time already. And on the left-hand side, you see simple queue service, which basically is a simple way to implement the queuing pattern that you have seen. And on the right-hand side, you see the simple notification service, and you can use that service to implement the publish-subscribe principle, for example. Why am I showing that? And the title of this session is Implementing it in 2023. We could have implemented all these patterns, and some of you may have done it 15 years ago. For example, when I started developing Java, we had JMS, and you could do this asynchronous queuing with Java messaging service JMS. But nowadays, we no longer want to spend time in operating and setting up these infrastructures, and serverless services help us achieving that. We reduce our maintenance effort and our efforts to operate those services by delegating it to the cloud provider, for example, or to someone else, and we can focus on the business logic and the discussion with our business on what are the events and how does the business logic behind looks like. And the best thing about that is I only pay for what I use with those serverless services, which means if I'm just going to try it and I'm not sure if it's the right concept, or I'm not sure how many users will actually use my product or my website, I have automatic scaling included, and the more I use, the more I pay, and if I'm not using it, I'm not going to pay for it. And durability and also availability and high security comes along with that. So, and to compare it to the classic model, on the left-hand side, you see if we set it up in the classic fashion, which means we do a capacity estimation on the maximum that we need, and we pay for everything constantly. Also, if it's idling around, we are still paying for that. And on the right-hand side, this is what we want to get, right? We only want to pay for what we really need, and this is what's provided by serverless services. Of course, you don't need to, you may have different preferences for providers or for things, how you want to use your IT infrastructure. So there are, of course, also open source solutions for that. And we at AWS, we also have open source solutions available for it in a managed fashion. On the left-hand side, for the queuing piece, you see RabbitMQ and ActiveMQ. Those are available as part of the Amazon MQ service. And on the right-hand side, you see Kafka. Max already mentioned it. It's also a very famous, increasingly popular solution to implement the publish-subscribe architecture. So, and then we have something else, a slightly different pattern, which is message routing. And why is that interesting for us as well? If you think back to the ordering architecture, not all events may be interesting for everyone. And by putting a message router in the middle that takes care of delivering certain messages or certain events just to dedicated subscribers that are interested. That's something an event router can do for us. And I brought actually an event router with me, which is Amazon Event Bridge. And you see again on the left-hand side, we have producers, so some AWS services, our own events that we feed into the event router, or even software as a service apps. And the event router itself has capabilities to apply certain rules to it. So depending on the source, it will route it to my target destination. Can be other AWS services, can be my business logic, or again, foreign destinations that I want to call there. So that was it with the theory. Now I brought an example so we get a better idea how this works in practice. And if you follow us, you may have noticed that we usually use unicorn examples. And in our case, we have here a company called Unicorn Properties. Unicorn Properties is a real estate company, and you can envision it as a typical real estate website, right? We need capabilities to manage the publications of property listings on those websites. We need, of course, contracts with the owners of that properties. And we also want to provide a view to our customers to look at approved listings and also see the images of those listings. And what we've built for that, I'm not expect you to identify each and every icon. It may look a bit complicated at first, but what you should get is we have 3 different areas. So we structured it, we looked at the different domains, we designed that for extensibility, and we built 3 different areas or domains of our architecture. And on the top left side, you see we have a domain called Unicorn Contracts. There's also logic inside to create a contract with an owner and to maintain that contract in a database. And then on the bottom, on the left bottom side, we have agent and customer. So basically, this is the web representation, another API that we use to display the listings on the website. And here on the right side, number 3, Unicorn Properties, that's basically the backend. So the approval logic, what happens when a contract changed, somehow identifying when there are status changes with contracts, and all the backend maintenance that's required for it. Then we have some other things around that. And in the middle is our event broker who works with routing the appropriate events to between the 3 different domains. And important to understand is also there is no single central database, right? While in the past, when I learned to develop software 20 years ago, it was like there needs to be a single source of truth. We don't want to duplicate data, and in our case, that would mean we have the single database. All contracts are in there, all properties are in there, and also all the data around there with referential integrity. Everything is inside of it. And this is no longer used nowadays, right? Duplication is okay, so we will see data duplicated, for example, from the contracts on the top left side. Data will be duplicated, at least partially, also in the Unicorn Properties domain in the backend in its own database. And that is okay. It's kind of the trade-offs that we are making to achieve that flexibility and loose coupling. Good. Enough talking. I will now show you a bit how this works. Just switching screens. Let's start. Where do we start? Okay, we need to get a contract for a property listing into my system. So basically, that's the first event that we start with. Overall, it's a REST request. So we started with synchronous HTTP calls, and this is a synchronous HTTP call to an API. So basically from the outside world, can be a UI where the contract was entered. We put in a property in Sweden here, Malmö, Main Street, and we send it to that API. This is Postman, just a tool to generate the API request. And if the Wi-Fi works, we see we get a confirmation back. with some properties here. The contract was created. We got an ID back, and it's in status draft. So what happened behind that, and this is what we can see here if we go there. So we hit an API gateway that actually exposes the methods, like the contract resource is here, and this API gateway is my entry point to my architecture in this case. And when I call this this API gateway, there is behind it, we have a serverless Lambda function. It's not essential for this here. It could be a container on Kubernetes. It could be a plain virtual server or something like that. Just something where my compute is, my business logic is running on. And now I see here that this Lambda function is actually some code, right? So we look at some code. This is a developer conference, and you'll get the link to the source files later on. As said, this is Java. We'll also have an example in Python, TypeScript, and .NET. You don't need to understand every single line. I will just tell you what happens here. So this is our entry point. So we get into this business logic, basically extract the JSON that we've just received from my API request, go through here, create the contract, save it to the database, and in the end, you see here, there is a publish event line. I'll just mark it so we can better see it. There's publish event. And this publish event, what is happening inside of it, I will just go into it, and we land here. We see there's a contract status event. And this contract status event is just a plain object that we have designed in the way that we want it to contain certain information. And this is the contract ID, the time it was created, the status, and the property ID. And this event is then sent to my event broker. And how do I do that? To communicate with the event broker, I have an SDK, which is a software development kit, basically a library that I can just add to my application. In Java, I do it in Maven and Gradle. This is a dependency management. I just pull in that SDK, and I can use that SDK to call my event broker. And certain functionality like exponential backoff, some retry mechanisms are already in that SDK, and I can basically use it to call my event broker from where I want. I can even do it from my on-prem data center, from my local machine, or if I'm already in the cloud, I can use it from cloud to another cloud service. So, and once I do that, I just go back to our web interface. Once I do that, I will be here in my EventBridge service. So that's just the UI that we can use to figure out a bit more what's happening there. And what we see inside the UI is we have certain rules. And if we go to our event bus here, we see there are multiple rules configured in that for that event bus. And the rule that we are interested in first is we have here something that's called contract status changed. And if we investigate that rule, it's basically telling us the same name that we've just seen in the code. So it's a detail type contract status changed, which means that's a my contract status changed event. And by putting it in here, the rule knows, okay, if I receive that particular event, what should I do with that? So and it's coming from my unicorn contracts domain. So if you remember the architecture diagram, the one on the top left side. And then I have targets, and in targets I can configure where the event actually flows to. And this is my backend, right? The backend needs to know there's a new contract created, and it should do something with that. And this is also here in the code base. So you have a folder on the left side. You see it, a folder for each of the domains. There's a folder for contracts, a folder for properties, and a folder for the web project. And basically what happens next is there is some logic running that is receiving the event, and then they can process it inside the properties domain, similar to how we've done that. So, and what's interesting now is we have more rules here, and it's pretty easy for us to extend it. If someone's interested in contract status changes, we can just add another rule here and just plug it in without letting the contracts service know that there's someone else interested in my event. And this is what we mean with loose coupling. And just to give you a last example before we wrap up, here is another event which is called publication approval requested. And this is here linked to a different target, so not my business logic, but rather a process. And I just wanted to show you that. There may be the case that I have multiple things that should happen once an event arrives, right? And there was another talk about choreography versus orchestration. And this is a possibility to build this in a nice little diagram using the UI here. So I can basically build a workflow using that step function service that executes some business logic. We see here the images are verified, that there are no that there's no weird content on it. We verify that it's a safe image that we can publish. And in the end, what we can do, after we finish that run, we can publish another event. And this can be either the publication is declined or the publication is approved and completed. And then we end that, that flow here. So, yeah, in terms of time, that should be it for the run-through. Let me just get back to it. So here are actually the links to the source repositories, and we will also publish the slides later on for the different options. So those are on GitHub. Feel free to try it out. We also have a workshop with instructions that we can that you can run through on your own, or you can also do it with us if you are interested. And if you feel that example wasn't a one that resonates well with you, we also have another one which is a managed care plan. And for managed care plan is basically you have a care provider, certain availabilities, like there's a available meeting on Thursday, and on the other hand you have the patient looking for a dentist appointment on Thursday, and they both want to negotiate the appointment. And this is something that we implemented using the open source way. So while EventBridge is an AWS service, this one is implemented using Kafka. And you also see there is a different type of database inside of it. So that could be also interesting for you, is also available on GitHub. All right, what should you take away besides these links and our wish that you get more asynchronous with your architectures and more loosely coupled in the future? You can really get greater developer agility from it by decoupling it. There are less dependencies between your development teams. You can increase your fault tolerance by using these services, and overall, if you go for a serverless solution, and event-driven architectures and serverless architectures, really they love each other. You can also lower your total cost of ownership because you are wasting less resources. All right, so we have just 1 minute left for questions. Any questions? Yes, please. We have it.
Thank you. I have a question regarding the events that you talked about regarding sparse or full events. Do you have any preference regarding that, or is it the use case based?
I think from yeah, you always want to have the minimal data in it because if you have a full-blown event, right, it can be a lot of data flowing around, and it depends on the use case, I'd say. What would you say, Max?
Yeah, so in general, so if you have the full events, you usually hear a lot about event carried state transfer. So sometimes it is useful if you have, like, for example, if you want to create a different read representation of something that was translated. So let's say you have an order, right, but you want to maybe store it that it can be more easy searchable, for example, in a different format. Then you might want to need all of those kind of details of the initial order. You store it so that it's more search optimized in another kind of service. So in general, if you have like data kind of replication and putting that on a different kind of read models, like CQRS is a common example, then usually you have this full kind of events being transferred. I think the question you would need to ask is it very common that the consumers might need additional data? Because if you only provide the ID of the order, then the consumer need again to query something else, right, back. And if that's always happening, essentially, then again you create that coupling back. So I think you need to evaluate really on the use case on how much downstream service you might cover with your current event structure.
Yeah, I think you want to avoid that you receive the event and the next thing you do is doing a REST call to the one that sent you the event to pull the missing data. That's kind of an anti-pattern. But always carrying the whole state around would be also not nice, so it needs to be something in the middle.
Thank you.
We're also available for questions afterwards,
in
case you want to chat. I think we're out of time.
Let's finish up on time. Thank you for being here. And if you are interested to run through this workshop with us, you can also reach out to us. We have account teams, not only us, delivering it, also in Sweden or Denmark or wherever you are from. Thank you for it.
Thank you very much.